All right, welcome everybody. This is the second talk of Asmita Mukherjee in our CTMP seminar series. As you can see, the title is Probing Gluon TMDs in Shape Side Production and Processes at the EIC. This is a very exciting topic in light of the EIC actually, right, being in production, so to speak. There is actually money spent on building that. But let me first repeat quickly the introduction of our speaker. Asmita Mukherjee received a PhD from the Science Institute of Nuclear Physics in India and had then several postdoctoral positions in Europe, one at the University of Regensburg, where we met for the first time, the University of Dortmund in Germany, and then in the Netherlands at the University of Leiden. She moved back to India in 2005 to accept the faculty position in the physics department at the Indian Institute of Technology in Bombay, and has been a professor in that department since 2015. She has received a Humboldt fellowship and at the University of Tuebingen in Germany, which is really a very prestigious award that allows you to maintain contact with that institute in Germany for a while. And she has already given us a first introductory talk, giving us the background on all manner of distribution functions that are used in order to analyze events and cross-sections of observables in experiments like this. And today she promised us to give us the lowdown on actual developments and on new things that she is doing right now. So please take it away whenever you're ready.
Thank you, Heribert. So let me start the second talk. So in the first talk, I gave a short introduction on the overall field of research, which is very exciting area in hadron physics in present days. And in particular, with relevance to the upcoming electron-ion collider at Brookhaven National Lab in the US. And in today's talk, I will be discussing some of the interesting research projects that I have been doing here at IIT Bombay with my students and postdocs, which also have relevance for this EIC. So in the first talk, I introduced the quark TMDs. So let me just give a brief recap. At leading twist, there are 8 quark TMDs. So on this line, on this row, you can see the polarization nature of the quarks. And on this vertical row, you see the polarization nature of the nucleon. So this F1 is a TMD when you are probing unpolarized quarks inside unpolarized nucleon. G1L when you are probing longitudinally polarized quarks inside longitudinally polarized nucleons. And so this is called helicity distribution, and these ones are transversity distributions. So as we saw, TMDs are functions of X and KT. However, if you integrate over KT, the intrinsic transverse momentum, you get back the collinear parton distributions. And if you do that, out of these 8 TMD, only 3 collinear distribution remains. These are the unpolarized distribution, helicity distribution, and transversity distribution. So the other 4 TMDs actually vanish when you integrate over transverse momentum. Out of these 8, 2 TMDs are of particular interest. This one, H1 pop, is called Bohr-Mulder's function. And this one, F1T pop, are called Sievert's function. These 2 functions are have some different kind of properties. For example, they are odd under time reversal. And so these give valuable and interesting informations about the quark and gluons distributions inside the nucleon and their correlations with spin and angular momentum, as we are going to see. Also, we said that different TMDs are probed in experiments in some observables called asymmetries. Basically, these TMDs, different TMDs, contribute in different azimuthal angle asymmetries. And that is how they are probed in experiments. From these experimental data, people have extracted TMDs. So the extraction of these quark TMDs is not that well at this point, but there is quite a good advancement in the extraction of unpolarized TMD as well as the Sievert's function up to N3LL. These are a few of the references. There are many other references in the literature. Similar to quark TMDs, there are gluon TMDs. Like we have both quark and gluon collinear parton distributions. Like that, we have quark and gluon TMDs also. At leading twist, there are 8 gluon TMDs. So again, this vertical column is the polarization of the nucleon, and this horizontal row is the polarization of the gluons. If you integrate over transverse momentum, only 2 of the gluon TMDs would survive, the unpolarized gluon distribution and gluon helicity distribution. There is no gluon transversity distribution. However, in terms of the TMDs, there are transversity distributions. There is also a gluon-Sievert's function, which is odd under time reversal. And there is also something similar to the quark-Bohr-Mulder's function. In this case, it probes the linearly polarized gluons inside an unpolarized proton. So in my talk, I will mainly concentrate on this gluon-Sievert's function and linearly polarized gluon distribution. So we will see more of them. Now, in contrast to quark TMDs, very little is known about gluon TMDs. So this is the operator structure of gluon TMDs. So they can be expressed as bilocal operators. You see this field is at 0 and this field is at psi. Since we are talking about TMD, so psi can be having non-zero psi minus as well as psi pop. So bilocality in the longitudinal as well as in the transverse direction. So I discussed this gauge link or Wilson line in the context of quark TMDs. These Wilson lines basically make this kind of operator structures gauge invariant. And it can be shown that in order to make this structure gauge invariant, you need not 1 but 2 Wilson lines. So that makes the process dependence of gluon TMDs more involved than quark TMDs. So there are quite a lot of work on the gauge link structure of gluon TMDs. Now, let me discuss the process dependence of TMDs and how it is related to this Wilson line. So I will give a simple example and I will discuss it in the context of quark TMDs. Now, suppose we are considering a semi-inclusive deep elastic scattering where we polarize the proton in transverse direction. So this is basically the schematic diagram of this process. So there's a lepton, there's an electron, incoming electron, it scatters. So this incoming electron and the scattered electron forms what is called the lepton scattering plane. And all the azimuthal angles are usually measured with respect to the lepton scattering plane. So what are the azimuthal angles in this case? First of all, we are observing a hadron in the final state. So there is a transverse momentum which has an azimuthal angle. Then the proton is also transversely polarized, which also has an azimuthal angle, which I call phi s. So phi h is the azimuthal angle of this pH, the hadron, and phi s is the azimuthal angle of this transverse spin of the target. Now, the differential scattering cross-section of this semi-inclusive process can be written in terms of this phi h and phi s modulations. So different terms have different kinds of modulation. This is cos phi h modulation. This is cos 2 phi h modulation. And each of these modulations come with a coefficient. And these coefficients depend on the TMDs as well as the final state fragmentation function. If you calculate this cross-section, you will see that the coefficient of the sine phi h minus phi s, this is the coefficient FUT, will actually depend on the quark-Sievert's function convoluted with the unpolarized fragmentation function. So if experimentally somehow or theoretically we can extract this particular modulation sine phi h minus phi s, we can get information on the quark-Sievert's function. Actually, that is what is done, and this kind of extraction is called constructing weighted asymmetries.
Sorry.
Yeah.
On those F coefficients, what are the subscripts denoting? The U's and the T's and the two U's? I don't think.
Yeah, so these basically denote the polarization states of the target. So here it has some information of this transverse polarization, whereas it is unpolarized. So these are somehow some shorthand notations. They are introduced just to distinguish each of them.
Okay, thank you.
So we also discussed a bit about quark-Sieverts function in the last lecture. So Sieverts function TMD was first introduced by Dennis Sieverts in 1990. This is related to the probability to find an unpolarized quark inside a transversely polarized nucleon. It includes the correlation between the quark intrinsic transverse momentum and the transverse spin of the proton. Also, in some model calculations, it has been shown to be related to the orbital angular momentum of the quarks, and that is how people have thought to connect it with this spin sum rule. However, these kind of connections cannot be shown in a model-independent way. A very nice summary of this discussion can be found in this paper. And as I mentioned, this is a T-odd function. And for this kind of T-odd functions, gauge length plays a very important role. In fact, it can be shown that unless you take into account the gauge length, Sieverts function will be 0. Now, one has to remember that gauge length is not particularly associated with TMDs. Gauge length is also present in collinear PDFs. The operator structure of a collinear PDF is something like this: psi bar y minus comma psi 0. Basically, it is a bilocal in the light cone longitudinal direction. So you can choose a gauge length which runs in the light cone minus direction, and such gauge length will involve this A plus component of the gauge. So in the popular light cone gauge, A plus equal to 0, this gauge length would become unity. However, in a TMDs, the bilocality is both in the minus as well as in the perp direction because the operator has this kind of structure. So even if you choose light cone gauge, you cannot completely make the gauge length unity. There will be the transverse part of the gauge length situated at the light cone infinity, the part of the gauge length that contains A part. In fact, that is the part that plays very important role in these T-odd functions, for example, the Sieverts function. Okay, so such TMDs would be 0 if the gauge length is not taken into account. So it was first investigated and shown in the context of a model by Blott, Huang, and Smith. But then John Collins wrote another paper where he showed that this is related to the gauge length. Now, how do we get the process dependence in the Sieverts function? Let us consider two well-known processes. This one is the semi-inclusive deep elastic process. This is electron-proton. In the final state, we observe a hadron in addition to the lepton. And this is the Drelian process. So from these kind of diagrams, this is basically the gauge length at the level of one gluon exchange. The actual gauge length comes because of multiple gluon exchanges. This is just an expansion of the gauge length up to one gluon exchange, because I just want to illustrate the difference. So as you see in the left-hand side diagram, so in semi-inclusive deep elastic scattering, the gauge link or the gluon interaction happens in the final state. Whereas in Drelian process, this gauge link or gluon interaction happens in the initial state. So it is final state interaction in semi-inclusive deep elastic scattering and initial state interaction in Drelian process. If you write down the corresponding Sieverts function explicitly in terms of this gauge link, we will see that in semi-inclusive deep inelastic scattering, you will get a future pointing gauge link, whereas in Drelian process, you will get a past pointing gauge link. So that is what brings the process dependence of these functions. Because of this, it can be shown that the Sieverts function probed in Drelian process will be same in magnitude but opposite in sign compared to the Sieverts function in CD's process. However, this is an example of a very simple process dependence. In general, for more complicated and general processes, for example, some hadron production or two hadron production in proton-proton collision, there is complex gauge link structure, and this TMD factorization in terms of TMDs is not always guaranteed. Are there any questions here?
Yeah, good.
Okay, so now let's discuss a bit about linearly polarized gluon distributions. Linearly polarized gluon distributions were first introduced by Mulders and Rodrigues. As I said, they probe linearly polarized gluons inside unpolarized proton. The operator structure of unintegrated gluon distributions or TMD gluon distributions can be different in different processes because of gauge length. And as I said, each gluon distribution, gluon TMD, contains two gauge lengths in contrast to quark TMDs. In the literature at small x, these are denoted by Weizsäcker-Williams gluon distribution and dipole gluon distribution. These are the two simplest process-dependent gluon TMDs. Weizsäcker-Williams gluon distribution contain both past or both future pointing gauge links, and dipole distributions contain one past and one future pointing gauge links. These are also called F-type and D-type distributions, and each of these distributions contribute in different processes. There is an extensive literature on unintegrated gluon distributions in small x physics. So out of that, linearly polarized gluon TMD basically measures an interference between an amplitude when the active gluon is polarized along x or y direction, and a complex conjugate amplitude when the gluon is polarized in y or x direction in the unpolarized hadron. And as we are going to see, it affects unpolarized cross-section as well as generates a cos 2 phi asymmetry. Now, similar to quark-Sieverts function, we can also define gluon-Sieverts function. This gives this generates because the distribution of quarks and gluons in a transversely polarized proton is not left-right symmetric with respect to the plane formed by the momentum and spin directions. This generates an asymmetry, which is called Sieverts effect. And as we said, this is a T-odd function, and for the T-odd functions, the gauge link is very important. So this, through the gauge link, it is highly sensitive to the color flow of the process and whether it is an initial state interaction or a final state interaction. And as I discussed earlier, in some models, the Sieverts function is related to the orbital angular momentum of quarks. However, unlike quark-Sieverts function, very little is known about the gluon-Sieverts function, although they are known to obey a positivity bound. So I'll discuss about it later. And depending on the gauge link of the operator structure, there can be two different gluon-Sieverts functions, F-type and D-type, depending on whether it is both plus plus or minus minus gauge link or 1 plus and 1 minus gauge link. Plus and minus means future and past pointing gauge link. There is a phenomenological sum rule, which is known as Burckhardt sum rule. This states that the total transverse momentum of all quarks and gluons in a transversely polarized proton is 0. So although not much is known about gluon-Sieverts function, using Burckhardt sum rule, one can get some constraint on gluon-Sieverts function. However, it has been found that it still leaves some room for the gluon-Sieverts function. That is, it need not be 0. It can still be about 30%. And secondly, D-type gluon-Sieverts function is not constrained by it. So the purpose of this talk is to discuss a line of processes, mainly Jepchai production processes in electron-proton collision that can probe these gluon TMDs at the upcoming electron-ion collider. The advantage of electron-proton collision and this kind of process is that in this case, only one type of gluon TMDs will contribute, namely the F-type gluon TMD, where it is 1 plus and where it is both either future or past pointing gauge links. This makes things simple because, for example, in proton-proton collision, there are often interference of two different types of gluon TMDs, and one then has to disentangle them. So EP scattering processes are simpler in this way. So gluon TMDs in Jepchai production processes. So Jepchai production can give a good estimate of gluon TMDs. It was first discussed by us in 2012 and also in 2017 for a simple inclusive, semi-inclusive Jepchai production in EP collision. Since then, there have been an extensive literature and quite a lot of progress has been made in the theoretical side. There is also some data from COMPAS. Here, what happens is that when the outgoing Jepchai, if we consider only semi-inclusive Jepchai production, in the final state you observe the lepton and the Jepchai, you have to observe the Jepchai in low transverse momentum region, because in this region, TMD factorization is expected to hold. On the other hand, when you observe the Jepchai at large transverse momentum, collinear factorization is applicable. In the intermediate region, results from these two formalisms should agree or match. So TMD factorized description of the process actually needs some kind of smearing effects coming from this transverse momentum inclusion in order to do this matching. So these kind of smearing effects are usually taken into account in something what are called TMD shape functions. The perturbative tail of this shape function can be obtained through a matching procedure. Again, recently there have been quite a lot of progress in this direction, And the matching coefficient for this semi-inclusive gypsy production process have been calculated. The other kind of processes where gluon TMDs can be probed is back-to-back production of gypsy and, for example, photon or jet or pion in the final state. You observe the gypsy and almost back-to-back, you observe another particle or jet. You have to observe these two particles in almost back-to-back configuration because here in this kinematics, TMD factorization is expected to be valid. And the small scale, as I said before, in processes where you probe TMDs, it is necessary to have a large scale and a small scale. For this kind of process, the small scale is provided by the transverse momentum of the pair, the transverse momentum imbalance. The varying the invariant mass of the pair, the scale evolution of the TMDs can also be studied. However, for this kind of back-to-back production processes, the smearing effects through matching and the shape functions have still not been calculated. They are not available in the literature. Let us consider the simplest of these kind of processes where we observe back-to-back gypsy and photon in the final state. They're not exactly back-to-back. We need to have some transverse momentum imbalance between them. So this proton in the initial state, it's electron-proton collision, and the proton can be unpolarized. It can also be transversely polarized or longitudinally polarized. So at leading order, the diagram that contributes here is like this. It is a virtual photon-gluon fusion process. And through this quark lines, you get a gypsy. This is formation of the gypsy in C-bar fusion. And then there is a photon coming out in the final state, which you are observing. So this is the frame that we choose. This is Q mu is the momentum of the virtual photon, P mu is the proton, L mu is the lepton. So sum of the kinematics, so Q square is the virtuality, S is the center of mass energy, and Y is the fraction of momentum carried by the virtual photon, lepton fraction of lepton momentum or energy carried by the virtual photon, and XP is the Bjorken variable. So one can show that gypsy production in this process will be mostly in color octet channel, and gypsy production in color singlet channel in virtual photon-photon fusion is suppressed due to a larger gluon density. So it has to be a color octet channel because of this outgoing photon. This carries no color. So in this kinematics, as we say, we can use TMD factorization, and the cross section can be written in this way. So L mu nu is the leptonic tensor and phi g is the gluon correlator inside the proton. So this is basically probing a gluon inside the proton. This includes the gluon TMDs, and H mu rho is the amplitude for the production of gypsy. In the literature, there are different formalisms to estimate the production of gypsy. There are mainly three different models or framework to calculate gypsy production. One is color evaporation model, then there is color singlet model, and the most widely used is the NRQCD. So in our calculation, we have used NRQCD to calculate the gypsy production rate. Here, the heavy quark pair is produced in the hard process either in the color singlet or in the color octet configuration, and then they hadronize to form a color singlet quarkonium state of given quantum numbers through soft gluon emission. There is an extensive literature on NRQCD. This is an incomplete list, so there's much more theoretical studies. So the hard process is calculated perturbatively, and soft process is given in terms of what are called long distance matrix elements. And these long distance matrix elements are determined from data. The LDMEs are categorized by performing an expansion in terms of the relative velocity of the heavy quark. And we assume that this relative velocity is quite small, that is V is much, much less than 1. And then the theoretical predictions are arranged in double expansions in terms of V as well as the coupling alpha S. So this is a schematic diagram of this NRQCD-based gypsy production in virtual photon-gluon fusion. So this is the incoming virtual photon and gluon. Then there is this hard process where C-bar is produced, and this C-bar emits soft gluons to form this non-perturbative gypsy with the correct quantum number. And this blob is basically the long distance matrix element. This blob or the long distance matrix element describes hadronization of the Q bar states, which can be formed in any color and spin configuration in the hard process, but they have to form the gypsy in the final state with the correct quantum numbers. So all these things are mapped into this blob or LDME. So in our QCD factorization, this AB part 2 partons going to Jebshai can be written in this way. So this is the hard cross section which one calculates perturbatively. So AB goes to C bar in some quantum number n, and then this is the LDME which basically gives the hadronization of this C bar pair. Okay. So now let us come back to the gluon TMDs in Jebshai and photon production. So we are observing the Jebshai and photon in almost back-to-back configuration, which means that their difference of the transverse momentum is quite large. So this capital K-pop is quite large, and the sum of the transverse momentum is small. So QT is much, much less than K-pop. So if you use inner QCD to calculate Jebshai production, one can show that at leading order, only one color octet state 3s1 contributes. There's no contribution from color singlet state. This is advantageous because then the cross-section depends on only one LDME at leading order, and the asymmetry becomes independent of the LDME. So they are robust probes of the gluon TMDs. So this is the gluon correlator for an unpolarized hadron. So at leading twists, these depend on the unpolarized gluon distribution as well as the linearly polarized gluon distribution. And this is the gluon correlator for a transversely polarized hadron. So this depends on the gluon Sievert's function as well as some other functions. Okay. So if you calculate the cross section for this process in terms of TMD framework, you will get this kind of expression. So when your proton is unpolarized, you will get different kinds of azimuthal modulation, A0, A1, A2. And then this coefficient is the F1, the unpolarized gluon distribution. And then there are again a bunch of modulations whose coefficient is H1 pop G, that is the linearly polarized gluon distributions. And these are the coefficients A0, A1, A2, B0, B1, B2, and so on. These coefficients have to be calculated in inner QCD. Similarly, when the proton is transversely polarized, you will again get quite a lot of modulations. However, here is the Sievert's function. It depends on this. It comes with a sine phi s minus phi t modulation. Now, in order to extract one particular TMD, what one does is one constructs what is known as weighted asymmetry. That is, you multiply the cross-section by a weight factor, which is basically one of these azimuthal modulations, and integrate over the azimuthal angles, and you divide by the unpolarized cross-section. If you do that, what happens is that all the other azimuthal modulations will actually go away, and you'll pick up only the particular azimuthal modulation that you are interested in. In this way, one constructs various asymmetries. So when the weight factor is cos 2 phi t, one gets the cos 2 phi t asymmetry. And for this process, one can show that it is directly proportional to this H1 pop G linearly polarized gluon distribution. And in the denominator, you have unpolarized gluon distribution. Sine phi s minus phi t is proportional to gluon Sievert's function. Similarly, you can construct several other asymmetries as well. And these coefficients A and B are calculated in inner QCD. And only one color octet state contributes in the cross section. So we will need only one LDME to estimate the cross section, but this LDME dependence gets cancelled in the asymmetry because it is a ratio. Okay, so that is why it's a clean probe of gluon TMDs. So I said earlier that the gluon TMDs satisfy certain positivity constants. So these are the positivity constants satisfied by the different gluon TMDs. So the upper limit of these asymmetries can be obtained when one saturates this kind of positivity constants. That is, instead of less than equal to sign, you set an equal to sign. However, these asymmetries will also depend on the parametrization or model of the gluon TMDs, because so far they have not been reliably extracted from experiment, although some attempts have been made. There are different kinds of parameterizations available in the market. The oldest and the most widely used parameterization is based on a Gaussian ansatz. For example, for unpolarized TMD, one can use this kind of parameterization. So in this Gaussian ansatz, the main assumption is that the X dependence is factored out from the K-pop or QT dependence. And F1G X mu is basically the collinear unpolarized PDF at a scale mu, which can be taken as Jebshai mass square plus Q square. So this kind of parameterization was introduced in this reference. And this exponential has a width, which you can take to be about 1 GeV square. Similarly, for linearly polarized gluon TMD also, one can take this kind of parameterization in terms of this collinear PDF. And for Sievert's function, there exists a parameterization like this. So the parameters in this kind of models are usually fitted using data. So in our estimates, we have used this kind of Gaussian parameterizations. And using these are the kind of asymmetries that we get in the kinematics of the upcoming EIC for this back-to-back production of Jepchi and photon. So you see cos, this is a left-hand side is a plot of cos 2 phi t asymmetry, right-hand side is a plot of cos 2 phi t minus phi pop asymmetry. Both are sensitive to the linearly polarized gluon distribution. So both are plotted as a function of this transverse momentum imbalance at two different values of q square. It can be shown that this asymmetry does not depend that much on square root of s. It increases, gets a peak, and then goes down. It depends on q square. And the asymmetries are quite small. Then one can also estimate the Sievert's asymmetry using the Gaussian parameterization. Sievert's asymmetry comes out to be negative. And these two plots are for two different values of square root of s, center of mass energy of EIC. The left-hand side is for square root of s equal to 45 GeV, and the right-hand side is for 140 GeV. You can see that particularly for square root of s equal to 45 GeV, Sievert's asymmetry is quite sizable. So it is sensitive to the energy. However, it is not that sensitive to the virtuality, the large scale q square. And so this process is a good channel to probe the gluon Sievert's function. The next process that we are going to consider is back-to-back production of Jepchi and a jet. So this is the process that we will consider. This is the kinematics that we are considering is very similar to the previous process. That is this final state Jepchi and jet. In this case, in the order that we are considering, it is just a gluon that forms the jet. They are almost back-to-back with a little bit of transverse momentum imbalance. So in the previous process, Jepchi and photon, we had one Feynman diagram. Here at this order, we have 8 Feynman diagrams. So we have to consider all of them. And we use TMD factorization and also use NRQCD to calculate Jepchi production. However, we have also compared with the color singlet model. So this is the reference of our work. So this is the amplitude of the process gamma star G going to Q bar, and this Q bar forming a Jepchi plus G. And this gluon in the final state forms the jet. So the amplitude in NRQCD can be written in this form, where psi L Lz and is basically the wave function of this quarkonium state with a given angular momentum. This is the Clebsch-Gordon coefficient, and this is the quantity that is related to LDME. This operator O, Q, P, psi, and K, this is the operator that comes from the Feynman diagram. So this includes the sum over all the Feynman diagrams, the 8 of them together with the color factor. And PSSZ is the spin projection operator, because in NRQCD, we assume that the C bars pair in the hard process can be formed in any color and spin configuration, and then it emits soft gluon to make the Jepchi with the correct quantum number. So these are the spin projection operator for spin triplet and spin singlet states. And using all these things, one can calculate the cross section. This is the form of the cross section. Again, there is a leptonic tensor, there is a gluon correlator, and this is the amplitude for Jepchi production that I have given in the previous slide. So this is the form of the amplitude. So one has to plug in this calculation of the Feynman diagrams as well as the LDMEs. So one can show that here multiple states will contribute. Contribution will come from the color singlet state 3s1 and color octet states 3s1, 1s0, and 3pj, where j can be 0, 1, or 2. So different LDMEs will contribute to the spin asymmetries. As I said before, in NRQCD, the relative momentum of the charm is small. What we do here is that we Taylor expand the amplitude about k equal to 0. The first term gives the S wave contribution and second term gives the P wave contribution. Now, formation of the bound state Jepchi from the heavy quark pair is encoded in the non-perturbative long distance matrix elements. As I said, these are obtained by fitting data. There are different sets of LDMEs available in the literature based on the calculations of different groups. So we will use some of these standard LDMEs, and we also show a comparison. Now for this process that I am talking about, the upper bound of the asymmetries, that is asymmetries by saturating the positivity bound, have been already discussed in this reference. Again, we have used the parameterizations of the gluon TMDs. The asymmetries will depend on specific parameterization used as well as the LDMEs. So in this work, we concentrate on the cos2phi asymmetry, which is sensitive to the linearly polarized gluon distribution. Just a reminder, we are considering almost back-to-back configuration, that is, sum of the transverse momentum of ship psi and jet is small and the difference is quite large. So QT is much larger than KT. And this cos2phi asymmetry is just this weighted asymmetry. And these coefficients B0 and A0 are we are calculating in inner QCD. And this is the linearly polarized gluon distribution. This is the unpolarized gluon distribution. So we can calculate the asymmetry using the Gaussian parameterization of TMDs like this. So the width of the Gaussian, earlier we took 1 GV square, we can take a somewhat smaller width. However, there are more parameterizations recently of these gluon distributions that do not assume a factorization of the X dependence and KT dependence. One of them is by Alessandro Bacchetta and the Pavia group, which is based on a spectator model, where this spectator model result is integrated over a spectral function over this range m to infinity, where m is the hadron mass. And in this spectator type model, one does not assume that this X dependence is factors out from this QT dependence of the TMDs. So this is interesting. And the expression of the unpolarized distribution and linearly polarized gluon distributions comes out to be like this in this model. So we have used both these parameterizations in our estimates, as well as we have calculated the upper bound of the asymmetry. Also in the last talk, I have said that like the collinear parton distribution, TMDs also depend on the scale of the process. So there is a scale evolution of the TMDs. However, evolution of TMDs is not similar to the evolution of collinear parton distributions. TMD evolution was first done by Ibath and Rogers in 2011. There are quite a lot of papers by now on TMD evolution and different ways to achieve TMD evolution, a comparative study of different ways to do evolution. One can also see the book by Collins, where there's a nice discussion on it. Basically, these TMDs are evolved in impact parameter space like this. So there is a perturbative kernel for this evolution. There is also a non-perturbative kernel of the evolution. And the perturbative part of the kernel is given here, where QF, the final scale for our process, is given here. The non-perturbative part of the kernel is basically a phenomenological answers. So we have in our work assumed these answers, or we have used these answers from this paper by Scarpa et al. And we have also used BT star prescription to prevent the initial scale to be larger than final scale at low BT. So basically, these TMDs should evolve in a finite BT range. It cannot go to very low BT or to very large BT. So large BT is very small KT and very low BT means very large KT. So large KT region is basically the collinear region. There one should match the TMD framework with the collinear framework. So there are different prescriptions to ensure that the scale evolution of TMDs lies in the required range. Using all these expressions, one can write down the final expression of this unpolarized gluon TMD like this and linearly polarized gluon TMDs like this. And one can calculate the asymmetries in different parameterization and also the upper bound. So left-hand side, the two plots are calculated in NRQCD, where we took into account both color singlet and color octet contributions, whereas right-hand side is a color singlet contribution only. The orange band is the upper bound, and this dotted line is the spectator model-based parameterization by Bacchetta et al. So you see in all plots, the spectator model-based estimate actually coincides with the upper bound. That happens because of the particular kinematics of the process. We have taken square root of S to be 140 GeV, which is relevant for EIC, and this is the rapidity and KT region. However, Gaussian parameterization gives a lower asymmetry, and if you use TMD evolution, the asymmetry decreases significantly. Okay, and also by comparing left-hand side plot with right-hand side plot, you can see that the color NRQCD gives a very sizable estimate of the asymmetry in absence of evolution, whereas in color singlet model, the asymmetry is very small. One can also study the contribution to the asymmetry coming from different states. As I said, the asymmetry depends on the TMD parameterization. However, it also depends on the specific LDME sets chosen. There are different LDME sets available in the market. So this is a comparison of the asymmetry coming from different LDME states. And we have also shown the contribution coming from different states in the final state. So left-hand side is when we took the LDMEs from this reference, and right-hand side is when we took the LDME from this reference. So this magenta line gives the total contribution, the magnitude of the total contribution, and the other lines shows contributions from different states. You see for this particular LDME set in the left-hand side plot, the major part of the contribution comes from 1s0 state, whereas in this other case, there is basically equal and opposite contribution coming from these two states. One is this blue dash, that is 3pj state, and this yellow dash dot, that is 1s0 state. So one can directly see that this magnitude of the total asymmetry also depends significantly on the LDME sets chosen. Another process that we considered is a Jebshai and pion production. This is again very similar to Jebshai and jet production. However, the gluon in the final state fragments into a pion. So this is the process that we are looking into. So I did not discuss in the previous two cases the estimate, the contribution from the quark initiated process. I only discussed this gluon virtual photon fusion process and the final state Jebshai. But in principle, there can also be contribution from this quark channel like this. Virtual photon and quark interacting, giving a Jebshai in the final state. And then this quark, in this case, forms a pion. In fact, here we explicitly calculated both quark and gluon contributions to the process. And we found that in the EIC kinematics, contribution from the quark initiated process is very small. So it is quite reasonable to assume that the main contribution here comes from the gluon initiated process. And this kind of asymmetries are good probes of gluon TMDs. Now, slight notations here, because we have a pion in the final state, there are different kinds of momentum fractions involved in the final state. So this Z pi is the momentum fraction of the pion with respect to the virtual photon, and Z is the momentum fraction of the pion with respect to the fragmenting quark. So Z is related to Z pi like this, Z equal to Z pi by ZA. And these are the expressions of the momenta that we have taken. Now, using TMD factorized framework, one can calculate the cross-section as well as the asymmetries. So since here there is a pion produced in the final state, there will be a fragmentation function for the pion. Again, sorry, is there a question?
Sure.
Is there a question? Sorry.
No, I'm banking my questions at the moment.
Okay. So this is the amplitude for Jebshai production. This is again the gluon correlator. This is the leptonic tensor. And this is the fragmentation function for pion. Now we are using a TMD factorized framework. So one would assume that the fragmentation function here also would be a TMD fragmentation function. However, what we have done is that we have assumed that in this back-to-back production of Jebshai and pion, the transverse momentum of the pion is much, much larger compared to the intrinsic transverse momentum of this quark with respect to the pion. So that is why we have integrated this intrinsic transverse momentum here, and the final expression depends on the collinear fragmentation function. The unpolarized cross-section here has different azimuthal modulations, and that this is the transversely polarized cross-section. So we have taken proton to be both unpolarized in one case and transversely polarized in the other case. And these A0, A1, A2, B0, B1, B2. So these are the coefficients that we calculate in NRQCD. So like the Jebshai and jet production, here also different states will contribute. And contribution from each state will be accompanied by a different LDME. like this coefficient A0 will get contributions from 3s1 color singlet, 3s1 color octet, 1s0 color octet, 1s0 color, and 3p0 color octet, and so on. So we have to incorporate all these contributions and all these LDMEs. Including all these things, the expressions of these coefficients A0, for example, A0, B0, A1, B1, they are very lengthy. So I have given the smallest of these coefficients here just as an example. I believe we have given all the coefficients in our paper. So the upper bound of the asymmetries can be calculated by saturating the positivity bound. The upper bounds do not depend on TMD parameterization. So this is a plot of the upper bound of the cos 2 phi asymmetry, left hand side, and right hand side cos 2 phi t minus phi pup. Both of them are sensitive to linearly polarized gluon distribution. So this blue line is the ratio of sigma q by sigma pup, sigma q by sigma, that is showing the contribution of the quark initiated process. And you see, we have plotted it as a function of k-pop. K-pop is the difference of the transverse momentum of J and pion. And in most of the range of this k-pop that we have considered, this contribution from the quark initiated channel is smaller than the gluon initiated channel. And this left-hand side plot as well as the right-hand side plot, you see, depends on Q square, the virtuality of the photon, and the specific kinematical range. Overall, both the asymmetries are quite sizable and can be good probe of the gluon linearly polarized gluon distribution. Next, we also estimate the asymmetry using Gaussian parameterization. In Gaussian parameterization, the magnitude of the asymmetry decreases somewhat, but still it is sizable. It's about 15% here, cos 2 phi t asymmetry. I forgot to mention, we have taken square root of s equal to 140 GeV, and we have used this particular LDME sets. And we have also plotted the asymmetry as a function of the transverse momentum imbalance. So here the asymmetry increases as a function of QT, becomes a maximum, and then decreases. This is cos 2 phi t asymmetry. This is cos 2 phi t minus phi pop. This is using Gaussian parameterization. This is an estimate of the Sievert's asymmetry in the same process. So left-hand side is a plot at square root of s equal to 45 GeV, and right-hand side is a plot at 140 GeV. So we have shown the contribution from quark-initiated channel, gluon-initiated channel, as well as the total. Sievert's asymmetry is negative, and as we see in most of the kinematical region, the quark-initiated contribution is very small compared to the gluons. So this is again Sievert's asymmetry as a function of QT. Again, you see the contribution from quark-initiated channel is very small. And Sievert's asymmetry is also quite large, about 15% negative. Left-hand side plot is for square root of s equal to 45 GeV, where the asymmetry is bigger. And right-hand side is for square root of s equal to 140 GeV. This brings me to the summary. We have discussed theoretical estimates of azimuthal asymmetries in back-to-back production of Jepchai photon, Jepchai jet, and Jepchai pion production in EP collision in the kinematics of the upcoming EIC. We have used NRQCD and color singlet mechanisms to calculate the Jepchai production rate. In Jepchai photon production, only one LDME contributes. Asymmetry is independent of the LDME choice. That is why it is a robust probe of gluon TMDs. However, this statement is valid only at leading order, and at next to leading order or higher orders, it will depend on multiple LDMEs. Cos 2 phi asymmetry here is small, but Sievert's asymmetry is quite sizable. In Jepchai jet production, there is a significant contribution to cos 2 phi asymmetry in NRQCD. However, in color singlet mechanism, the asymmetry is much smaller. And we have shown that TMD evolution decreases the asymmetry quite a bit. The asymmetry depends on the LDME sets chosen as well as the parameterization of the gluon TMDs. For asymmetries in Jepchai pion production, contribution from quark-initiated channel small compared to gluon. Actually, this is the fact for the other processes as well. Overall, we have shown that these Jepchai production processes at the upcoming electron-ion collider will be a good channel to probe the gluon TMDs. That is all. Thank you.
Thank you. Thank you for the broad spectrum of individual things that you've covered. I think we have seen more than we can chew right at the moment, but I still do have a couple of questions.
Okay.
But if anybody else in the audience wants to go first, you guys go.
Yeah, I have sort of three, but two are very related. So I don't know if I misunderstood in the beginning, but you said that the asymmetries that you calculated when you used the weight function and
Yeah.
sort of integrated over the angle.
Yeah.
My understanding that those were independent of the LDMEs because it was a ratio.
Mm-hmm.
But later on, you're telling me that the asymmetries that we're looking at are dependent on the LDMEs that we pick.
Yeah, so when I said they do not depend on the LDMEs, that is for a particular process, which is back-to-back production of Jepsai and photon. Here, what happens is that it gets contribution from only one LDME. Okay, when there is only one LDME, you can just cancel the LDME in any asymmetry from the numerator and the denominator.
Okay.
But when there are contribution from different states, so each of these LDME is multiplied by a different coefficient and it is convoluted. Then you cannot just cancel like that between the numerator and the denominator. For the other two processes, Jepsai jet and Jepsai pion, that is the case. So the LDME dependence cannot be cancelled in the numerator and denominator of the asymmetry.
Okay, that makes sense.
Yeah.
I had another question about the parameterization of TMD. We looked at sort of two versions, one with the Gaussian where the X dependence factors out, and the model. I guess an obligatory question is why Gaussian? You said it was an ansatz from I believe, and just because it's a good function to use. And does the spectator model make any kind of claims about that same shape?
Yeah, so the spectator kind of models, by now there are several spectator kind of calculations for gluon TMDs available in the market. Actually, we also have a model. So it is more general than the Gaussian parameterization because as you correctly pointed out, the assumption that the X dependence is factored out from QT dependence is just an ansatz. So it may not be true. So that is why it is interesting to consider models where this factorization does not happen. However, for the numerical estimates, as I have shown, the spectator model in our kinematics at least agrees with the upper bound of the asymmetries. So whereas this Gaussian parameterization satisfies the upper bound, but it lies below it. So it does depend on your parameterization. So I think the spectator model parameterizations are still to be developed further. These are very new things.
So is it in some way obvious why this saturates the bound? Or did you just find it out after the fact?
No, it actually saturates the positivity bound because our estimates are in a particular kinematical region. In this kinematical region, it happens to saturate the positivity bound, whereas it is not guaranteed to do so if you consider an observable in a wide kinematical region.
Okay. Sorry, any? Cool.
Yeah, I had I think a more broad question. So it seems like you've shown results from different models. I'm curious, when the EIC turns on and there's data, what do you learn? Is the point to sort of rule out some of these sort of more phenomenological models or further constrain the fits? And then I guess that you're hoping there's some sort of physics to learn that's independent of the models. Is which of those situations is the
so this is actually a very interesting question. So you see, these kind of processes and the kind of observables that I was talking about depends on two things. One is the TMDs and the parameterization of the TMD used. The second is LDMEs and also the shape function, which we did not include in this process. So LDMEs are also not very well known. There are different sets exist in the market. So one can perform two different kind of studies. One can calculate or one can estimate these asymmetries and make and obtain some constraints on the LDMEs by knowing the TMDs, or one can fix the TMDs, or one can gain information on the TMDs and knowing the LDMEs. So both can be probed, and in the literature there are discussions on how to do both. There are a set of variables which are sensitive to the LDME sets chosen and not that sensitive to TMDs. So these kind of observables you can construct and measure at EIC if you are interested to learn about LDMEs. Then there are observables which are sensitive to TMDs and not that much on LDMEs. So these you can use to probe the TMDs.
Okay. And I guess in principle, you would want like a combination of all these things to constrain both.
Yeah. Yeah.
Okay, thank you.
All right, so could you go back again to the gauge link question, right? Can you give potentially, yes, absolutely, potentially simple criterion, what makes initial state and what makes final state contributions show up as relevant for the gauge links that you put in?
Yeah, so basically, this semi-inclusive triplastics process, you see this gluon exchange is between this quark and the blob, and this quark is the final quark which comes up after this scattering with the virtual photon. So this is a final state gluon exchange. Whereas in Drelian process, this is the initial state quark.
Yeah.
And this gluon is exchanged between the blob and the initial state. So that is why it is an initial state interaction. And when you write down this operator structure of these TMDs, you will actually have to you will have to incorporate these multiple gluon exchanges. In this diagram, you see only one gluon exchange, but in general, there will be multiple gluon exchanges. So when you resum all those contributions, you will get that exponential gauge link. That is where the process dependence and the color dependence come in.
So usually, right, you get final state contributions if you do not have final state cancellations, if you don't have a tag vertex, right, somewhere. If you do have
it will depend on your process. It will depend on your process. Sometimes you'll get both initial state and final state interactions. It's completely process dependent.
Yes, absolutely. Now it's a question about, usually it's a question about tagging, right? If you write your perturbation theory in terms of old-fashioned, right? Old-fashioned perturbation theory, where you don't fully transform the time direction, so to speak. That is usually what allows you to distinguish, to see final state cancellations, right? This is, but at the moment, it's not totally obvious to me how I see this in your diagrams. Maybe I need to think a little more. Yeah,
so there are extensive literature here. So these are the two references where you can see details of this calculation. In particular, this Moore, Mulder, Spillman paper in 2003 have discussed these things in detail.
Okay, so I'll
also they're there in Collins's book.
Yep. Okay. All right. Thank you. The other thing was the effect of evolution. How do I need to think about that? That effect you're describing. The evolution is between what kind of scales and why does it push things down?
Yeah, actually, for the particular observable that we have talked about, it is very simple to understand. Okay. Because we have constructed an asymmetry which is sensitive to linearly polarized gluon distribution in the numerator and unpolarized gluon distribution in the denominator. So evolution gives the linearly polarized gluon distribution at first order in alpha s, whereas it is at 0th order in alpha s in the denominator. That basically pushes the asymmetry down for this particular observable.
Okay. Okay. And so the non-evolved and the other curves were non-evolved in a sense. Is that what I'm telling you?
The other ones are not evolved.
Okay. So there is a scale mismatch that you're taking away when you evolve this. Is this correct, or am I misinterpreting?
Yeah, so basically these are different approaches. Here we assume that the parameterization gives the TMDs at the scale at which I am calculating, which may or may not be correct.
Okay. Okay. Thank you. I
Thank
think
you.
that's what I'm seeing there. Do we have any other questions? Well, then let's thank you again.
Thank you.
Yeah, we can stop recording, I think. So